Okay, welcome again to this second session of the WAFERS workshop. So second workshop on validation and verification of future cyber physical systems. And it's also a pleasure to welcome Professor Edson Tavares de Camargo for being the chair of this second session. So we have 4 papers also in this session, and okay, I think we can start whenever you want. Thank you.
Thank you very much, Leonardo. Hello, everyone. It's a pleasure to me to be here. I see very nice papers here, and we'll start with the first paper, bit vector support in the Terra formal verification framework. So I think the authors are here. As I said earlier, I don't know if I will pronunciate your name correctly, please. So if you present yourself.
Mihai. It's pronounced Mihai.
Mihai, okay. Nice to meet you, Mihai. Welcome to the workshop. So Mihai is a master student of computer science engineer at the Budapest University of Technology and Economics, Hungary. Former intern at CERN, researching formal methods, software verification and testing, and applying the research in industrial projects targeting software verification at BUTA, developer of the open source verification framework Terra. So Terra is a framework from the University of Hungary. So please, we can start.
First of all, I would like to welcome everybody. My name is Mihai Kovács from the Critical Systems Research Group of Budapest University of Technology and Economics, Hungary, and I would like to present the work I did with Ákos Hajdú and András Vörös, in which we implemented bit vector support in the TITA formal verification framework. Nowadays, different kinds of software systems surround us more and more. An interesting aspect is safety-critical systems in which a failure can have dire consequences. Huge financial cost, a catastrophic environmental effect, or even the loss of human lives. Examples range from airplanes to nuclear power plants, or even the vehicles that everyone drives. Thus, ensuring correct behavior is an imperative task during the development process, and usually extra emphasis is put on the verification and validation steps. When it comes to the methods of software verification, testing is an obvious choice. In a nutshell, testing checks the behavior of the system for given inputs, and basically during testing the developer or the tester seeks the inputs that lead to errors. Testing is a mandatory step of the development by all standards regulating the development of safety critical systems. However, it has a major downside. As Dijkstra put it, program testing can be used to show the presence of bugs but never to show their absence. Meaning that testing can be used to find errors, but if during the testing we did not find any, it is no proof for their absence. On the other hand, formal verification is a fundamentally different approach. Formal verification checks the mathematical model of the software and explores the whole state space of the program. It is unfortunately a research-intensive task, and it suffers from the phenomenon called state space explosion, meaning that even the simplest program can have a huge or even an infinite state space. However, formal verification can find errors in the state space that have a minuscule chance of actually happening, thus it maybe even was missed by the testing process. And it does that automatically, and since it explores the whole state space of the program, it can even prove the absence of errors. Model checking is a formal method that awaits a formal model and a formal requirement and checks whether the requirement holds on the model. If it does, it produces a mathematical proof for that. And if it does not, then a counterexample. Counterexample describes a single scenario in which the requirement fails. Since we target software verification, we need a way to formalize computer software, let's say C code, which shows the control flow automaton formalism, or CFA for short for that. A CFA is a graph-like structure of locations and edges, with the instructions of the program can be found on the edges. As for the requirement, we usually designate some of the locations as error locations, and we state as the requirement that no error locations are reachable. It is worth noting that error locations can be generated from assertions, and also that in case of a CFA, a counterexample is a path in the CFA that leads to an error location. Next, I would like to introduce a commonly used model checking algorithm. Counterexample guided abstraction refinement, or CGAR for short, is a widely used method. To combat the problem of state space explosion, it utilizes abstraction. The core of the algorithm is the so-called CGAR loop that has two distinct phases, the abstractor and the refiner. The task of the abstractor is to explore the abstract state space and look for error states. The abstract state space is basically an over-approximation of the reachable states, so if the over-approximation does not contain any errors, then the program is said to be safe and we have a proof for that. However, if it does contain errors, then the refiner needs to intervene. Basically, there are two options why there are errors in the abstract state space. Either because it is a concrete error, and in that case the program is unsafe and we have a counterexample for that, or the abstraction was too coarse and it needs to be refined. In that case, the refiner refines the abstraction, removes these spurious states from the abstract state space, and the abstractor continues to explore it. However, there are still challenges in how to model computer software. Take the simple C code as an example. In this, we define a variable a with a value of 255, increase the variable by 1, and then assert that it should be 0. If we model a to be a natural number, then we have an equation stating that a should be 255, another version of a prime should be a plus 1, 256, and then a prime should be 0. We can see that this set of equations indeed does not have a solution. However, if we take into account that in C the variables are stored on a finite amount of bits, in case of unsigned cars 8 bits exactly, and they overflow, then we have a completely different model. In this case, we have a statement saying that a should be 255, a prime should be a plus 1 modulo by 256, and then a prime should be 0. And in this case, these equations indeed hold, and the model is satisfied. Another problematic modeling question is how to handle bitwise operations. Bitwise operations are common in embedded systems, in which case a variable might not be a number but a bit field, and mathematically implementing them is extremely difficult. Take the example on the right, in which case we have a bit field as an input and we want to extract the value of the third bit. If we model the bit field as an integer number, then the equation to extract the third bit is extremely ugly. We have to take exponents, we have to take integer parts of divisions, etc. And if we take into consideration the bitwise and then bitwise OR and other bitwise operations, then things quickly escalate. In summary, we have two rivaling ways of modeling computer integers, either using mathematical integers or bit vectors. In case of mathematical integers, the arithmetic is based on the mathematical set of integers, so a value is always signed, there are no unsigned values. A variable has an infinite range and it does not overflow. We can see that it does not model the exact semantics of computer variables, but algorithms tend to opt for them because they are more effective to compute with. In case of bit vectors, a computer integer is a list of bits, and their arithmetic is based on the arithmetic of computers. So the values are stored in 2's complement, have a fixed length, a finite range, and they overflow. Unfortunately, they are less effective to compute with. At the bottom, we can see a simple example. In case of mathematical integers, if we want to add 3 and 5, the result will always be 8. However, in case of bit vectors, if we add 3 and 5 with unsigned arithmetic, then the result will be 8. But if we add them with signed arithmetic, then because of overflow, the result will be -8. Finally, let me introduce Theta, an open source, generic, and modular model checking framework developed by our research group. It can receive its input in multiple formalisms. It can handle computer software with CFA, system models with symbolic transition systems, and timed automaton with its extended timed automaton formalism. The core of Theta is a cigar algorithm that has configurable abstraction and refinement strategies. The algorithm pulls first-order satisfiability queries to SMT solvers and uses the answers for the verification process. Currently, Theta is already integrated with Microsoft Z3 solver. To implement bit vectors in Theta, we had to extend it at two places. First of all, we had to introduce new expressions in the formalisms for bit vectors, addition, subtraction, signed and unsigned comparison, and bitwise operators. And we had to map the new bit vector expressions to the SMT solvers. Fortunately, SMT solvers support bit vectors, and the fixed-size bit vectors theory is part of the SMT-lib standard as well. And after that, everything else should work out of the box. Unfortunately, we hit a roadblock at refinement. The refinement process receives an abstract counterexample as an input, and outputs, basically depending on the abstraction, but usually a list of predicates. The task of the refinement is to determine the feasibility of the abstract counterexample, meaning whether the abstract counterexample is a concrete counterexample or not. And if not, then it should refine the abstraction. The refinement process uses the SMT solver for that. To be more precise, it uses the Craig interpolation capability of the SMT solver that is able to find the cause of infeasibility in SMT problems. However, a major hurdle for us was that Z3 does not support interpolation with bit vectors, and since it dropped its support a couple of years ago, it is not expected to do so in the coming years. To circumvent this issue, we basically had two options. The first is a new refinement strategy that does not rely on interpolation at all. An advantage of this method would be that it could be used with other solvers as well that do not support interpolation at all, for example Z3, CVC4, Booleftor, or Yikes, which are among the best solvers based on the annual SMT solver competition. An other option would be to integrate a new solver with Theta that support bit vector interpolation, and there are solvers that can do that, for example MatSat and Princess. For the sake of this paper, we decided to stick with the first option, but we also worked in parallel on the second, and we released an alpha SMT-lib support in Theta 3.0 last month. As a new refinement strategy, we introduced Newton refinement. As input, it receives an infeasible abstract counterexample and outputs a list of predicates just as much as Craig interpolation. Newton refinement is actually a group of 8 variants, and they all build on either weakest precondition or strongest postcondition predicate transformers and unsatisfiable cores. For the sake of generosity, it is worth mentioning that SMT solvers must support unsatisfiable cores, but support for them is much better than for interpolation. On the right, you can see a simple example for Newton refinement. On the leftmost column, we have an infeasible counterexample, a trace in which we set a variable x to be 255, increase it by 1, set the value of a variable y to 2x, and then assert that x should be 0. Next, we take the mathematical model, and in this case, we can see that this is indeed unsatisfiable. And if we take the unsatisfiable core, then we can see that basically the statement that writes y actually has nothing to do with why this set of statements is unsatisfiable. Then we have an optional step to abstract these unnecessary information away, creating an abstract trace, and use strongest postcondition or weakest precondition to calculate an inductive sequence of assertions for that. In this example, we used strongest postcondition, so starting from true, we first set the x to 255, increased it by 1 to be 256, y does not affect the value of x, then asserted it to be 0, and the result is false as it does not hold. And from that we have a list of predicates. Finally, we evaluated the Newton refinement with examples from the software verification competition. First, we did not use bit vector inputs as we wanted to compare its effectiveness with Craig interpolation. The results can be seen on the table on the right. If we use predicate abstraction, then we saw that the Craig interpolation option was better, and the best Newton variant was the one that used the abstract trace and weakest preconditions. The others were far behind. However, if we used explicit value analysis, then 3 variants were better than this Craig interpolation one, and amongst them the best was again the one that used the trace abstraction and weakest preconditions. Finally, we evaluated with bit vectors as well. We used examples that were handcrafted by us and also examples from the software verification competition's dedicated bit vector category. The results can be seen on the right, and again we can see that the Newton variant that performed best was the one that used trace abstraction and weakest preconditions. In conclusion, we developed bit vector support in Theta, and thanks to that, new kinds of systems became formally verifiable, namely embedded systems. Moreover, we implemented new refinement algorithms that can be used for other purposes than bit vectors as well. As for the future, we plan to integrate SMT-lib compliant solvers with Theta, and as I've said, alpha support has been available for the past month for that. We plan to utilize bit vectors, Newton refinement, and these SMT-lib compliant solvers in our bid at the software verification competition of 2021 as well, which is happening right now. Thank you for your attention.
Thank you for your presentation. So now we would like to hear from the audience. Let's make a deal here, guys. Let's make questions to the presenter, okay? So I will start. So someone would like to start? So I will start. No problem. In the paper, you state that the small scale evaluation of the introduced features was executed. My question is: it will be necessary a medium or large scale evaluation to collect more results of the features that were implemented?
Yes, and we partially doing that large-scale evaluation as we entered the software verification competition. The deadline was this Monday, so the results can be expected in the coming days, and it will contain a large-scale evaluation of how Newton refinement works in general and how we can tackle bit vector problems in general.
Okay, thanks. More questions?
Yes, don't be shy, but I also have a question. If someone has questions, please. My question is about, I'm curious about the limitations, So which are the limitations about these bit vectors? So can you, for example, combine properties with bit vectors? Can you hear me?
Yes, I lost you for a second when you started talking.
Okay. Now I was mentioning it's my curiosity is about limitations of these formalization of bit vectors properties. So, for example, can you combine bit vectors properties with any other properties, or if can
generally yes. Generally yes. So we can combine it with arrays as well, and what's an interesting area of study is if we combine bit vectors with floating points. There are usually not so great solution for that as of now, but it's an interesting area of study to provide one.
Interesting. And also the size of the bit vector doesn't matter, or is it still?
It does matter, and it really depends on the SMT solvers. So an easy way is to divide the 32-bit length bit vector to 32 Boolean variables and basically do a addition with those 32 variables. This will not scale at all, but there are smarter solutions than that. But still, usually verification tools opt for the usage of integers because they are much more efficient to compute with.
Yeah, sure. That's very interesting. Thank you.
Well, congratulations again for your work, Mihai. Thank you very much for your presentation.
Thank you for the opportunity.
Okay, everyone. So now let's choose the next talk. Next talk, the paper V-Model Adaptation for Space System in Light of the ECSS Standard, with Professor Regina Moraes, Tânia Basso, e Eliane Martins. Eliane Martins is here.
Yes.
Hello, Eliane. How are you? Nice to see you
Fine.
here. Eliane Martins was a professor at Institute of Computing at Unicamp, and it's now retired, but is still collaborating with the university. Her areas of interest are software testing with focus on embedded system testing. She participates with other colleagues of the Advanced project. I would also like to add that Eliane is one of the major contributions to the field of the test and fault tolerance in Brazil. So welcome, Eliane.
Thank you very much for your kind words.
In this work, we present a process model for the development of cyber physical systems, CPS. And for this, we adapted the V model, which is popular in software engineering, and with the ECSS, which is a standard for the development of space systems. And this is a joint work with University of Coimbra, with Regina Moraes, and me and Tânia are from Unicamp. This is the outline of the presentation. First, we present context and challenge, then the architecture of a satellite mission, the ECSS life cycle, our proposal, and conclusions and future work. During the last decade, the space area has evolved significantly thanks to advances in the technology of embedded electronics. This gave rise to new products like, for example, small satellites like nanosatellites. As an example, there is a CubeSat that is shown here in this figure. Well, with the hardware miniaturization, and there are demands for new services, and this increases software responsibilities, making these space systems software-intensive systems, okay, that are embedded in small space. And in contrast, VNV activities for these satellites do not comply with the traditional standards for larger missions, but the space areas has requirements that cannot be ignored and need to follow strict development and VNV process. So the challenge is how to establish VNV activities for these embedded software that are compliant with existing standards and, if possible, in a cheaper and faster way. To help understand a bit more what is the context, Let's give here a brief overview of the architecture of a space mission. A space mission generally has 4 segments. The launch segment, which is used during the launching of the satellite. The space segment, which is the software and hardware embedded in the satellite. The ground system and the user that prepares and configures the mission. Okay. The main part of the space here we focus on the space segment. The main part of the software part in special of the space segment is the onboard data handling subsystem, which is responsible for the command and control of the whole space mission. It controls the payloads, which are the subsystems that implement the missions of the satellite, and also a set of embedded electronics like electric power, attitude control, and so on. And also it communicates via a network with the ground segment. So the software intensive systems is the OBDH, and that's why the standards generally focus on the quality of the development of this part of the space mission. Since we are using the ECSS in our solution, let's take a brief overview of this standard. Well, the standard describes the system development, which comprises 7 phases. For each phase, there are 1 or more reviews required, as you can see here. So, for example, we start with the mission analysis and needs identification. That is, after this phase is ready and the document is generated and the mission definition review is performed. Okay. Until the system enters in operation, there are 2 reviews, one prior to entering operation, which is the operation requirements review, and one prior to launch, which is the flight readiness review. Of course, after the disposal phase, there is no sense in having a review. The standard also provides some physical models that are used in VNV activities. The engineering model, which for the hardware, for the satellite, which is a prototype of non-qualified components of the satellite. The qualification model, which has the satellite components integrated in the flight structure for testing purposes, and the flight model, which is the components in the flight structure already assembled for testing and for launch. Okay, so these are the main elements of the ECSS that we will use in our solution. The proposal uses the V model that is very well known in software engineering, and it was a process developed or proposed in 1995, and since then it has been used and extended to cope with system areas also. The process comprises 2 parts that are connected. In the left part, we can see the evolution of the development cycle, and in the right part, we can see the testing phases. And the arrows indicate that tests are prepared during the development, okay, and also the occurrence of tests can cause the requirements to change and so on, the corresponding phase to change. And also it can comprise reviews, verification between the phases of system development. And this is completely compatible with ECSS guidelines that requires reviews at the end of each phase. Also, the V-model was used as part of the advanced project as a proposal for the validation of CPS systems. So this is our V-styled model. I say V-styled because this part here is the horizontal line is not exactly forms a V-model, but anyway, it is based on that, okay? This model has different layers or ties, in which the outmost one is corresponds to the different mission phases of ECSS presented some slides ago. The dark blue one contains the review activities required for each phase, as you can see here. This is phase D with its 2 reviews, and this is phase E with its 2 reviews also. The middle part is corresponds to hardware development. The blue part corresponds to software development. And the horizontal part represents the integration between software and hardware for different embedded components that are integrated individually. Then when they are all integrated, we can have the system tests, acceptance, and so on. Okay, so this is the way we have to represent the reviews, the hardware development, and the software development. In this slide, we present some related works. Since it is a short paper, we only choose the ones that are closest to what we are doing. The first one presents a V-model for CPS systems in various areas, and their focus is specifically in requirements and requirements modeling for the various components that can be software and so on. And they do not follow a standard for any specific area, and like in our case that we follow ECSS, and the reviews are not explicitly considered in their model. This model is discussed in more detail in the paper because we use it to compare with our work. Another one that we choose was CPS for space area, and they use as an example an aircraft vehicle, and they discuss the challenges and what technologies are used to address these challenges during the development, and they also do not mention an international standard. Well, to conclude, we presented the V-model for space systems, and that addresses hardware and software development according to the phases recommended by the ECSS standard. It makes explicit the reviews required by ECSS standard along the system life cycle, as well as the testing activities. It highlights the integration of various embedded subsystems that constitute the CPS, and is a first draft for the advanced project, okay, in the sense that we are basing this for space systems, and the idea is to extend for other CPS systems. This work is a first draft of a process model for space systems, so in this sense it needs some adjustments with INPE staff. In this way we can then detail each activity and artifacts produced by each activity, and the description of the artifacts that are needed for the review tasks.
Okay,
before.
Thank you, Eliane, for your presentation. Okay, everyone, we have a question. Question from the audience.
Yeah, maybe I can start. Oh, sorry.
Hi, Anna. Hi, Anna.
Hi, Anna, please.
How are you?
Hi, everybody. Eliane, what do you see? What do you mean by make some kind of adjustment with the INPE's participant or engineering? What do you mean by, what do you advise for adjustment in the V model?
Well, because we propose that based on the development for larger satellites, okay, traditional ones. So we took every review and testing phase recommended by ECSS. But I saw, for example, in a previous work of the group, that for CubeSats, for small satellites, some of these reviews and artifacts produced for larger satellites are not necessary, okay? So that's why the model should be made adjustable to different space missions, because sometimes some activities and some artifacts are not necessary. But anyway, the other reviews and the documents and the steps necessary for review will be taken into account.
Okay. So I understand you didn't practice this. You didn't apply in a project.
No, not yet. Not yet. This is something that we will need to do, of course, in order to have this as an option for VNV develop for IoT development with VNV embedded, okay, in the process. This is also another point that needs to be taken into account.
Okay. Thank you. That's it.
Okay, it was nice to see you, Anna.
Nice to see you too.
Thanks, Anna. More question? Leonardo? Okay.
Yes, just a quick question. Eliane, I've seen that in the model you have these three lines, no? Three models that go in parallel. I did not understand if you are also looking at the interactions or dependencies, for example, between software and hardware, if this is something that makes sense to consider, and if you are maybe planning to do this.
Yes, this makes completely a sense, and some of the activities take the two lines of hardware and software because they are common activities for both. And of course, software sometimes have to wait, the software components have to wait for some model or something of the hardware to be ready for start, for example, testing and things like that. So this is something that we have to detail also, but it's something that is already in CSS, okay, in order to have the, and we have to adjust it to our V model as well.
I see. Understand. Thank you. Very nice. You are muted, Edson.
Yeah.
Thank you for our questions. Thank you, Eliane, for your talk, for your participation. It's nice to see, and you are very active, as I can see here for your talk.
Well, not as before, but anyway.
Okay. So next to the let's do the next talk.
Okay, thank you.
Thank you.
Thank you, Eliane.
Next talk, next presentation has the title Towards Simulation of CubeSat Operation Scenarios under a Cyber Physical System View. Danilo will be the presenter. Danilo is here. Okay, he's here. Danilo graduated in mechatronics engineer from the University of São Paulo, and later graduated with a Master Science in Space System Engineer and Management at Brazil National Institute for Space Research, INPE. During his time at INPE, he worked for the NanoSat BR2 CubeSat mission with minor participation in the Sport and Coron 1 Nanomirax missions. Currently, Danilo works as assistant engineer for Udrosat. So let's start.
Hello everyone, my name is Danilo. I'll be presenting today this work called Towards Simulation of CubeSat Operational Scenarios under a Cyber-Physical Systems View. This work was developed at Brazil's National Institute for Space Research in partnership with the Fault-Tolerant Systems Research Group from the Budapest University of Technology and Economics. So just a brief summary of what we're going to see here is I'll start with a brief introduction giving the context of the work. We'll describe how we generate the mission architectural model with the core of the work, discussing the simulation tool that we model for, and then going through how we actually create the model in the tool that we use. And then we'll discuss also the transformation plugin that was developed for this application, some application results in the CubeSat mission that we were working on, and then end with the conclusion. So, beginning with the introduction. So, space system engineering involves several different competencies and from multiple disciplines of engineering. Over the years, a lot of norms and standards were developed to guide the process in all phases of the space mission lifecycle. With the introduction of the CubeSat standard, for those of you who don't know, the CubeSat is a satellite of the NanoSat class, which is like 10 by 10 by 10 centimeter cube, and you can stack these cubes to make larger satellites, and you put the modules in a standardized way inside of them. So they were initially developed for capacity building and hands-on experience for students, so they usually don't carry fidelity to these norms and standards, and this is one of the reasons for this high mission failure rates that CubeSats have when compared to traditional satellites. Not the main reason, but one of the reasons. So in this study, we are tackling the lack of mission concept analysis, which is usually done in pre-phase A and phase 0. And these studies are usually done in concurrent engineering centers, which are facilities that concentrate specialists from different areas in a room or one more room in a conference room, that they work together in a brief amount of time to define the initial concepts of the mission, and you can have a large exchange of information between the professionals in the scenario. So this is an image of INPE's Concurrent Engineering Center called C-Prime. So in mission concept analysis, it's heavily supported by modeling and simulation. And one important part of this is balancing power and data budgets. So this involves modeling and simulation of in-orbit operational behavior so that you can do power and data budget analysis along the orbit. And this is used for verification of mission requirements. So this work in this context introduces a cyber-physical abstraction of CubeSat mission operation scenarios. So this is done to support this behavioral analysis. And we use architectural models based on SysML class diagrams for this application. And we use an open source modeling tool called Capella. We developed a plugin called C2F to automatically generate code from this model that we developed. And this code is used as input for the Forplan satellite simulator tool, which we'll describe in a second. So the main contributions of this work is first a structured mission architecture model in this context, defining the operation scenarios. And then the C2F, the Capella to Forplan plugin that was developed to automatically transform this model into the configuration script for the Forplan simulator tool. So let's go describing how we generate the mission architecture model, going through the simulation tool and the model in Capella. So first, let's talk about the general workflow of the whole approach. So we begin by defining the mission elements involved in a mission, describing the equipment operations, which we'll go through later. And then we generate the first mission architecture model, which outputs the class diagram, the initial meta model. And then we input the model parameters for this meta model, and we output the parameterized class diagram, which is the instance model. We then use C2F to convert the model into the simulator input, which outputs the simulator configuration script, which is in Julia language, and then we simulate the scenarios in Forplan, analyze these results, check if the requirements were met. If they weren't met, we go back, input different model parameters for the model, changing the scenarios, and then generate the outputs again, simulate it, analyze results. If the requirements are finally met, we use these results to drive further design implementations. So keep in mind, this is in the initial steps of the mission. So let's talk about the Forplan simulation tool. It was designed for verification of space mission concept of operations, which we call CONOPS, and to be used in phase 0 pre-phase A studies, as I mentioned. And it was developed at INPE's Space Mission Integrated Design Center, which is the concurrent engineering center called C-Prime. It performs functional simulation of satellites and associated ground segments to reflect operations scenarios of the mission under analysis. So here you can see the user interface during a simulation of a satellite mission, which with some equipment defined and the path along its orbit. So it generates a low Earth orbit environment and simulates the mission to define equipment operation, electrical power generation consumption, and data generation, data downlink to the associated ground segment. It was written in Julia, and it's based on what the developed satellite toolbox. So configuring Forplan, you have to use Julia language, of course, configuration script describing the mission elements, such as the orbit parameters, solar panels, equipment list, which is the equipment on board the computer, on board the spacecraft, the battery pack, the associated ground stations, and the equipment operation functions. So the equipment operation functions are the functions of each individual equipment, which describe when and where they're going to operate, how much power they're going to consume, and how much data they're going to generate based on a set of simulation parameters and internal conditions. So we defined 4 basic types, so we can use this model and automatically generate code for that. So the first one is an always on, which is the equipment is always turned on in a constant state, and equipment is on only above ground stations. So this is useful for some transmitters, for example. Some timed operation, so the equipment is periodically turned on and off. The parameters used for that define the on time and off time, and also the region of interest operation, so RORI op, which defines if the equipment is turned on and how it operates depending on a region it is above. So to configure it for Forplan, here's a snippet from the configuration script. So first you define, for example, here an equipment instance, which has the core method for it, defining it as an equipment. It has a name for it, the operation function, which describes how it's going to operate. For example, here's the on-ground station, has its internal parameters. So each operation parameters depend on which function it's going to use. So creating the model in Capella, which is the tool that we used. So this is the abstract model of the mission architecture model. So we defined a set of data packages and using class instances and using the properties of each class instances, so we can then retrieve the information in each of these data packages specific to what we're looking for. So data packages, class instances, and the properties inside of each of these class instances. We also defined a set of units just to have a reference here. So unfortunately, Capella only supports 1 meta level, so it's not feasible to instantiate elements in such meta models. So we can't define this as an abstract model and then instantiate lower levels of instances. So to overcome this, we defined for the plugin a well-defined set of rules. So hard coding the name of the properties, the classes, and data packages. So the C2F, the plugin looks for the elements that are containing these actual names. So here's just a snippet of adding, for example, property value. So we define the value here, and it gets assigned to the property, for example. So let's talk about the model transformation plugin called C2F. It was developed through a partnership via the Advance project. And we developed an Eclipse plugin for the Capella tool, which is called Capella to Foreplan. That's why it's C2F. So it traverses the model elements in accordance to the predefined rules and generates Julia code from the retrieved attributes based on the Foreplan configuration script that we're expecting. So for example, initially some Julia-specific programming constructs that are specific to the simulator as well, setting the simulation environment and imports as well. And then some predefined functions, for example, the ROI function, the timed operation function we can add here, and futurely some other ones. And then the objects that we instantiate. So for example, here are some ground stations, the equipment, payload, and equipment list. And then finally the configuration or the configuration options for example, the orbit that we're going to define, and then calling the simulation. It was built on top of Extend, which is a high-level language designed for model transformation and code generation. Here's a snippet of C2F going through the solar panels, for example, to extract the properties from it. So some application results for the Nanosat CBR2 mission. It's the second satellite mission of the Nanosat CBR program, which is a cooperation between Brazil's National Institute for Space Research and the Federal University of Santa Maria. It's a scientific and technological mission, so it aims to collect data to better understand the magnetic anomaly of the Southern Atlantic, also to collect data to understand the formation of plasma bubbles in the ionosphere. That defines one payload, which is the Langmuir probe. A second payload, which is a validation of an in-orbit fault-tolerant attitude determination system, which we call the SDATF, which is here. And also validate in orbit a radiation-tolerant FPGA and ASIC system, which is this payload right here. And also, the mission was to develop human resources with experience in space missions, so it was a lot developed by students at the time. So here is the resulting mission architecture model for the mission. So here we can see all the equipment instantiated inside the platform, a data package and payloads, the regions of interest, orbit parameters, solar panel array, and also the ground stations. So then after executing C2F, this is for example output code from it, just for reference later on. And so we used 3 different simulation scenarios to, well, more than 3, but resulted in 3. So here's just an example. So for the first scenario, we let all the payloads in an always-on configuration. So that would be like the maximum operation for all the payloads. Here you can see the configuration of the data package with always-on function for each of the payload. And however, it depletes the battery very quickly and generates a very large amount of data that we can't downlink to the ground stations. And here in the second scenario, we want to use a timed operation for each payload. So we just quickly change the operation function to the timed operation, give it the parameters for each one of them, so different operation periods and operation times for each of the payload. And then the results, we can see that the battery charge was maintained. However, it's still generating too much data. So after some iterations, we reached a third scenario, which was a valid scenario based on the requirements we had, which was defining the Langmuir probe as a region of interest operation mode over the AMAS, the magnetic anomaly, and the equator for the plasma bubbles, then one orbit each in a timed operation for the other 2 payloads. So here we reached a stable battery balance, power balance, and also data balance as well. So this was a valid scenario for us. So in conclusion, we presented here a workflow for operation scenario modeling and simulation of CubeSat-based space missions. It's meant to be used in phase 0 analysis and operation requirements and verification. We presented the C2F tool for automatic model transformation into the floorplan simulator configuration script, and the example application for the Nanosat CBR2 mission also was demonstrated. And these results from this final scenario drove the final implementation of the expected operations in the flight software. So by using the mission architecture model and the automatic code generation, the user is no longer required to understand the simulator source code, which can be quite tricky if you're not familiar with programming. And also you don't have to manually code the configuration differences. You just visually configure the different inputs and the properties. And so it's a more straightforward use of the simulator. It also allows for faster configuration and different scenario execution. So it leads to facilitated work. And so for future work, we envisioned to define a process to model user-defined operation functions, not only the 4 standard ones that we defined previously, and have this method in C2F to automatically generate code from this modeled function into a floorplan execution function. So thank you very much. I'll be happy to answer any questions.
We cannot hear you, Edson.
Thanks, Danilo, for presentation. So my net is
Danilo.
a little bit low now. So we have a question, Anna?
Yes, I have.
Please.
For Danilo. Let's waiting a little bit.
Danilo is here, not here?
Sorry, I didn't know if I should share my camera before.
Okay.
Hi, Danilo.
Hi, Danilo.
Nice to see you.
Yes, nice to see you too.
My question, in fact, is related to the last future work you cite in your presentation. It's related to how to create the scenarios. And but I have a question before this. How easy is to configure all the parameters necessary to create a scenario?
Well, to create a scenario, so once you've used the simulator, you see that there's not that many parameters. They're all listed in the abstract model that I've seen, and you just double click them, add the parameter values, save, and then automatically generate from a drop-in menu from Eclipse, which is just pressing some buttons and inputting the values. There's one slide in the presentation that shows exactly like how to input the values, and it's I mean it's fairly simple, much simpler comparing to if you want to open the code, locate where the function is declared, and then you have to go through all the software and understand it. That's my perspective.
Oh, okay, so you have to sit to configure each parameter, each value.
Yeah.
But do you have a defined some? I mean some configuration of equipment or subsystem. Do you have a predefined some profile?
Yeah, sure. I mean, every time you can import just, well, for example, this last for the Nanosat CBR2 mission, you can just import the last one, you open the model and everything will be defined there. So you just change some specific configurations that you'd like. For example, I want to use a different ground station. So you just put a different latitude, longitude, the baud rate for the ground station, and then there you have it for another simulation.
Okay. And concerning the scenarios, there are some guides to have scenarios of fault, of dangerous situations for the satellite or all subsystems.
We haven't considered this because again, this is for initial concept analysis. So you want to expect what initially what the scenarios of the payloads will be operating, how much data they'll be generating, how much power they'll be consuming. So then you can arrange how they're gonna orchestrate among them. To include that, you would have to describe it into the equipment operation function. So maybe add some faulty. So this equipment operation function, it gets analyzed every iteration of the simulator. So you would have to input some faults into this function at every iteration, and then you can so defining some conditions in some regions that it wouldn't work. So then you could have some analysis results of it not operating in that region, for example. That's at least my initial idea. I don't know if that answers your question.
Yes, it is. Okay, it's for initial analysis, not for safety or anyway, but it could be used in the future, I think.
Yeah, I think it just has to be thought about a little bit.
Okay, thank you, Danilo. Nice to see you.
Anna. Nice to see you too.
Thank you, Anna, for your question, the qualified participation. More question? Okay, Danilo, thank you very much for your presentation.
Thank you.
Now let's to the next presentation. The title is Towards a Robustness Assessment Methodology for IoT Systems. Bruno Jesus, Glauter Leite, Nuno Antunes. Bruno is here. Bruno is a PhD student at the Faculty of Science and Technology, University of Coimbra. Currently a researcher at Software and System Engineering Group at the Center for Informatics and Systems, where he develops research related to IoT systems, security, and robustness. The master degree was in computer science from the Federal University of Pernambuco, focusing on RFID technology and anti-collision protocols. He graduated in computer science from the Federal University of Alagoas in 2006. So let's start.
Hello, everyone. My name is Bruno Almeida de Jesus, and today I will be presenting the article called Towards a Robustness Assessment Methodology for IoT Systems, which was written with Glauber Leite and Professor Nuno Antunes. The outline of this presentation will be this. First, I will talk a little bit about IoT systems and some challenges. I will then talk about our proposed approach and assessment methodology. Finally, I will present the proposed scenario, the first functional prototype, and the conclusions. We can understand Internet of Things as a technological evolution that aims to connect everyday items to the Internet. In practice, the interaction of the IoT system with the environment occurs through the use of sensors and actuators. The sensors are responsible for gathering environment-specific information, for example, temperature, presence, humidity, sound. The actuators are responsible for acting in the environment. For example, opening a door or lowering the temperature. The gateway is responsible for the communication between the things through the different communication protocols. The gateway also supports things, integration, and communication. The cloud is responsible for managing IoT systems, including the generated data. So, why clients are being used? To help in one of the main IoT challenges, heterogeneity. Large amount of information passing by them. there are a considerable number of things communicating with each other by different communications protocols. We all know that security is important in any system, but in IoT is even more important. Things are available on every place, home, business, offices, and because of it, physical access becomes easier. IoT devices play an important role in many different aspects in the world, which makes the concern with security and privacy in the communication between them essential. It's important to provide security for all components by various perspectives. An example of the general architecture of an IoT system is often presented through this three layers model. At the network layer, we have the main component of our study, the gateway. But why we should secure IoT gateways? As we said before, all things should be secured. Gateway is also a thing, so it should be secured too. However, gateways are not a regular thing. If attacks are useful to this component, all the environment can be severely compromised. Because of it, gateways are high-value targets and should have the appropriate security attention. We also have the integration frameworks, are the main software component of gateways in an IoT systems. With this in mind, and considering this architecture, we've listed some challenges in implementing IoT systems. The first one is about the relation between security and resource constraint. How to lead with this relation. To achieve system security, some requirements are necessary. Due to the natural limited resource of the IoT components, it's relevant to start by studying the robustness attribute that leads us to the second challenge, that is related to the robustness of the software component. A function could be considered robust if it handles erroneous input and output arguments and still provides a meaningful error message. IoT environments are often susceptible to outside interferences and threats. A lot of information passing by the gateway. So the third and fourth challenges are related with the security requirements. We plan to discover what are the main security requirements and which gateways already meet them. For traditional network, one of the most important security requirements is authentication. That isn't different on IoT environments. We also intend to evaluate the authentication methods used by the gateways and how can we improve them. In order to perform a good robustness analysis in an IoT system, we proposed a realistic scenario that will be briefly described below. As I will detail on the next slides, we are performing some robustness testing in a realistic scenario, observing the behavior of system and protocols implementation. From the results, we aim to develop alternatives to software that aim to mitigate security and robustness problems. So we start to think, how could we perform a robustness testing on MQTT protocol implementations? For this purpose, we selected 3 questions regarding the behavior of the components. The first question is about the size and frequency of the messages. What is the behavior of brokers when receiving messages published with payload sizes larger than usual, and when receiving repeated publications of many messages in a row or simultaneously. The second question is about the number of clients. What is the behavior of the systems, integration frameworks, and protocol implementations when used by a very large number of simultaneous clients? And finally, the third question is about the malicious messages. What is the behavior of systems when used by malicious clients creating and publishing malicious messages? Now I tried to summarize on this animation the process flow to verify the IoT protocols and gateway robustness. We represent the interaction between these three system components: the broker, the integration framework, and the dashboard that will represent the data collected on system. First, we modify a message payload and publishes it under a topic on broker. Second, the integration framework will subscribe on the same topic. Third, the broker will publish the modified message. Here, we can check the behavior of the broker, and at the end, the integration framework will publish the message to the dashboard. Here, we also can check the behavior of the integration framework against the published message. Here, we present the first structure of the proposed scenario. Our scenario is an automated hydroponic system for growing vegetables. In this system, we have IoT components that control sensors like temperature and light, actuators like fans and LEDs, and hybrid controllers with sensors and actuators. In addition, we will also have a component that will host the MQTT broker and the integration framework. Finally, we will have a component that will help us to create messages that will be sent to the system, here called the injector node. This is the first functional prototype. Here, we have three ESP32 boards that represent the controllers mentioned in the previous slide. For the purpose of first prototype, the broker and integration framework were hosted on a computer. So, our focus on this study was to investigate the integration frameworks, also called gateways software. Our main target is to discover robustness issues of software components in IoT systems by testing its limitations when dealing with unexpected inputs. After this, we aim to discover the security issues on these components, mainly integration frameworks implementations. For this, more platforms were selected based on their level of similarity and application within IoT systems, because they work with cloud-based applications and distributed data sources. As a future work, we intend to assess each related vulnerability discovered and the security measures proposed for these vulnerabilities, assess also the security requirements and threat response. All of this because we considered security one of today's major IoT challenges. I would like to thank the opportunity to be here, and now I open the floor to questions and comments.
Hi. So let's That's question.
Yeah, I have a question. I don't know, maybe if I have missed in the video during the presentation. Is this approach specific to some protocol and some kind of hardware, IoT hardware, or I mean, what is the effort to adapt to other technologies? I mean.
Okay, Leonardo, thank you for your question. I don't know if you are hearing me. Yeah. Okay. At first, we will test with MQTT implementations and with a specific hardware on this representative scenario that we talk about. But yeah, we plan to diversify this. Also, these boards, we change protocols, use another protocols and our implementations. But at first, our proposal is use the MQTT, one of the most used protocols for this kind of scenario.
I see. Thank you.
I also have a question. Let me see if I understood correctly your work. Are you evaluating authentication? That's okay? With MQTT integrated. Authentication is the main issue, I think.
Yeah. It's one of the attributes that we will evaluate, but not just.
How other security issues are you evaluating in order to make a security gate DOS attack? I don't know if it was applicable.
Yeah. At first, Edson, we thank you for your question. At first, we will focus on the robustness of the system. At first, not considering external attacks like DOS or other attacks, but the problems that can arise by system malfunction or a kind of malfunction on one of the controllers and this kind of issues. But yeah, we also plan to evaluate in next steps other types of attack. I don't know if you answer.
Okay. Thank you, Bruno.
Okay.
We have time for one more question. Okay. Thank you, Bruno, for your presentation. Thank you, guys. So for Leonardo, it's up to you now.
Yeah. Yeah. We have. If you want, we have time for maybe questions or on the other presentations and papers also. If somebody, I don't know, some questions came into the mind of people. Otherwise, yeah. Some questions, no? Anna?
Oh, no, Leonardo, I'd like to say some words just to finish the workshop. Now?
As you wish. I have just a couple of, just one slide also, but yes, please.
No, just to finish, I'd like to thank you for the organization of the second edition of the WAFERS. I'd like to thank to you, to Nuno Laranjeiras and the Vinci Mona for the efforts to conquer the people, to write papers, and to be here to discuss, to present their ideas, their research. It was very good for the LADC, and thank you for all the work and your time to prepare.
Thank you. I would like to thank you. First of all, thank you, Edson, for participating here and being the chair of this session, and Tommaso also for the first session today. And I would like to thank all the people that sent papers and that are participating here. I see that we have a nice number of people for the workshop, and I was monitoring, we were around 16, 17 people, so it's nice for this workshop, which is the second edition. And I would like to thank also Nuno and Vince that they could not be here today, but they did also, they did a very nice work. And yes, I hope to see you maybe at WAFERS 2022, maybe. So just to recall, most of you know, because you are participating in the project, but this workshop was coming from this advanced project. So we cannot say it is supported by advanced because this project is suspended in the moment for the pandemics. So the European Commission said we cannot officially support the workshop, but it came from this project, which involves partners from Europe and South America. So Chini, University of Florence, University of Coimbra, Portugal, Budapest University of Technology and Economics in Hungary, that gave a big contribution to the workshop, as you say. Resiltech in Italy, Resiltech SRL, Los Andes University in Colombia, and the University of Campinas in Brazil, and INPE also in Brazil. So if you want maybe if you are someone is interested in these topics, you can find more details on this link of the project and contacts of the people that are working on these things. And so thank you, everybody, and I hope to see you at WAFERS 2022.
Good.
Thank you again, Leonardo. As we know, our community is small. We have a small community. Fault tolerance and tester is built by researchers, by few researchers. But what I see here was great work, and congratulations to workshop. I said to Guto last week or 2 weeks ago that the workshops did a great job in LADC, because we have many papers that came from the workshop. So participants that the workshops bring inside LADC. So it was a very important contribution. This workshop and the other workshop here in LADC. Thank you very much, Leonardo, Ana. I said that in name of the fault tolerant commission that I am representing in this moment. So thank you very much.
Thank you.
Edson. Yeah, it's still very good that we have a lot of workshop in LADC, and yeah. Okay, so thank you, everybody, and I think we can close here now. And again, thank you for attending and sending papers, presenting, and asking questions and answering questions. Thank you, everybody.
Okay, thank you. Bye-bye.
Thank you.
See you.
Thank you. Bye-bye.
Bye-bye.